Arthur Frank Harvey was born on the 21st of March 1910 in Ebbw Vale, South Wales. In 1929 he graduated from the University College of South Wales and Monmouthshire with a BSc in electrical engineering subjects, receiving the Page Gold Medal for the best students in the engineering department. The university described him as being the most brilliant student the department has had for many years, exceptionally brilliant and likely to go far. Dr. Harvey's early career included an apprenticeship at the South Wales Power Company, working as a technical assistant for Johnson & Phillips, and later getting his PhD at Oxford University. In 1960, Dr. Harvey won the IEEE Microwave Prize for his paper Periodic and Guiding Structures at Microwave Frequencies. He also wrote several papers and 2 books on microwaves and lasers. His work included research and development on millimeter wavelengths and coherent light techniques. Dr. Harvey died on the 26th of March 2006, but not without having left a lasting legacy. In 2010, the IET dedicated substantial funds left by Dr. Harvey to the creation of the Dr. A.F. Harvey Trust Fund. Dr. Harvey's terms were simple. The donation must aid the furtherance of scientific research into the fields of medical, microwave, radar or laser engineering. The IET's trustees agreed the funds would be used to offer an annual research prize covering all fields over a 3-year cycle. It is the IET's largest prize fund, with the winner being awarded an engineering research prize of £350,000. The prize fund's Search and Selection Committee searches for potential candidates from around the world, drawing on wide international networks. The committee draws up a shortlist of candidates from whom additional information is requested for further detailed consideration.
We are working on these tiny, small things which are called dielectric nanoantennas. What we are trying to achieve is some elements which can control light, and like that we can generate, for example, holograms which can move. And like that we can produce holographic displays and also some virtual and augmented reality devices.
So it will open some opportunities that we can test things that might be quite difficult in a traditional application to one of the funding agencies. So we can do a lot of new things and use this as an opportunity then to start many other new projects that will nucleate from this research prize.
I'm excited about my work. I love what I do. Every day I try to excel myself, what I did in the past, and we'll see, but it's baby steps, so I hope that in 1 year I will have something exciting to tell.
Dr. Harvey achieved great work in his lifetime. His legacy continues through the prestigious IET A.F. Harvey Engineering Research Prize.
I'm very excited to give this year's Harvey Lecture to you. I'm very honored to win this year's IET Harvey Prize. It's so nice to win an award for something you love doing every day. Before I begin, I'd like to acknowledge all of my students, collaborators that contributed to the research I'll show you today. Our group's research is really focused on trying to impact many different technologies. And if you look at some of the technologies shown on this slide here, it turns out that all of these light-based technologies, such as solar cells, displays, augmented virtual reality, and communications, they're all limited by our inability to manipulate light at the nanoscale. Now, interestingly, Faraday already found a solution to this problem all the way back in the 1850s. He noted that tiny little metallic particles of gold and silver show very strong colors, such as the vial here with colloidal nanoparticles. Gives this beautiful red ruby color, which later on was shown, as shown in the electron microscopy image on the left, to be due to gold nanocrystals inside this colloidal suspension, typically on the size scales of several tenths of a nanometer. If you take a light absorption spectrum, as shown on the left, where we plot the absorption versus the wavelength of light, which represents the color goes in this spectrum all the way from the violet to the greens, all the way to the red. you'll see that an absorption of this vial of gold nanoparticles made by Faraday shows a peaked absorption somewhere in the blue-green part of the spectrum. And because the purples, the blues, and the greens are strongly absorbed, the red light tends to be transmitted, giving this vial such a beautiful red ruby color. If one would have done this with silver nanoparticles, then it turns out that the resonance would have shifted further to the ultraviolet part of the spectrum, and the color of this vial would have been yellow. So interestingly, manipulating the color of tiny little particles, or the size of tiny little particles, could give us these beautiful different colors. The key to achieving such intense colors is related to resonances. Resonances, we know from the world around us, resonances are key to giving us very strong responses with just a little bit of effort. For example, the lady pushing the girl on the swing needs to just provide gentle tapping motions at a right frequency to get a large amplitude for the girl to swing left to right. Or a gentle touch of a guitar string can produce one beautiful note. This all happens at one very specific frequency, which in the case of the guitar tends to be the tone of the guitar note. And at that frequency, we can use this concept of resonance, which will be key to this presentation today, to get very strong optical responses. Also, the very strong optical response, as you saw in the color for the vial made by Faraday. Well, let us try and understand why there are optical resonances in nanostructures. If we look on the size scale bar on the left to orient us what happens at different size scales to the properties of metals, we recognize life-size structures such as a dust mite, things that we can still detect with our own eye, to tiny little micro-machined mechanical parts called MEMS, or the little pits of in a compact disc on the order of a micron wavelength. And below that scale, we go to the scale of viruses, atoms, and molecules. In going from the macro scale, from the millimeter scale to the nanometer scale, we pass a very important length scale in light, which is the wavelength of light. Wavelength, or light, has a natural wavelength in the visible part of the spectrum that is around 500 nanometers, or about half a micron in size. Think something like at least 100 times smaller than the size of the diameter of your hair. Now, the optical properties of metals completely change if we go from the macro scale, where we, for example, imagine a mirror that we look at every morning. This is how I see myself in the morning in the mirror every day. So you can see metals already look like have unusual properties even at the macro scale. But if we break that mirror in tiny little pieces, it turns out that if we pass the size scale of the wavelength of light, we start to see beautiful colors, as the example below from Naomi Hollis's group on showing tiny little gold nanoparticles that can produce, depending on their size and shape and how they're made, different colors, all the way from the visible spectrum all the way deep into the infrared. So something very special happens when we go from the macro scale to the nanoscale. The world becomes colorful, and I'll argue that these are resonances at play giving rise to such strong color. Well, if one wants to understand where the colors come from, we need to think about the excitations of plasmons in metal particles. Plasmons are collective oscillations of electrons, conduction electrons inside a metal. When a light wave passes by a metallic nanoparticle, here shown in yellow, the electric field that's associated with the light wave can start to set the conduction electrons in motion. Just like if we apply a battery to a little metallic wire, the electric fields can run an electrical current of electrons. Here, the electrical current driven by the oscillating electric field of a light wave will cause the electron cloud to oscillate up and down. producing strong charge displacements inside this metallic particle. As for example, the electron cloud is pushed down by the electric field, we'll see that because of charge neutrality, we leave some positive charge on top of the metallic particle. A moment later, we see that the fields are opposite and push the electrons upwards. So you get a sloshing of the electron cloud. Now it turns out that we can see that this actually occurs resonantly, so that we can get very large oscillations of the electron cloud. And to understand that, we can derive or use an analogy to a mass spring system, where we have a tiny little mass, in our case the mass of the electron, attached to a spring, and that spring pulls back the electron if it's displaced from its equilibrium position. Here, the electric field of the light has displaced the electrons, but there is a restoring force, the Coulomb force between the negative and positive charges, that's going to pull the electron cloud back, just like that spring in the mass spring system analogy. Well, it turns out that a mass spring system shows resonances. I can very subtly bounce a little mass in a spring. If I do it at the right frequency, called the resonance frequency, here noted as F resonance, I can get a very strong response of the oscillating electrons and therefore a very strong current. This current can cause, like in a metallic wire, absorption and heat if I run high currents through a metal wire, or also scattering by this metallic particle. So at this resonance frequency, I can very efficiently convert light energy to motion of electrons to then heat dissipation or light scattering subsequently. Now this resonance frequency, we can mathematically derive, is related to the spring constant C divided by the mass of the electron and the square root of that. So one sees if one has a light mass, the mass of the electron is extremely light, and a strong restoring force, and these Coulomb forces between negative and positive charges is very strong, we can get very high resonance frequencies. In this case, resonances occur in the visible spectrum of light. So over time, with the age of nanotechnology, we've become better and better at controlling these resonances through sizing and shaping. Here are examples of optical microscopy images of different metallic particles that are shown below the colorful red, green, and blue dots. Little triangles of gold give rise to red colors. Other circular or rectangular rod shapes can give rise to other colors. It's nice to see how we've been able to learn and develop the Lego blocks or the Minecraft blocks, if you like, that could be the basis for all sorts of nanophotonic artistry, where we can selectively start interacting with very specific colors of light. And this is really the art of nanophotonics, to control light scattering and absorption at will, at any color of interest. So these tiny little particles we'll call the basic building blocks, the Lego blocks, or in this case, we call them meta-atoms, and the meta-atoms are the blocks with which we can build more complex constructs that can manipulate light in more complex ways. As things have evolved, we've gone from examples where we have simple basic blocks of different size and shape we can manipulate by putting them together, or nowadays, as shown in the third image from the left, we can put many of these particles together and use the controlled light-matter interaction of these different sizes and shapes to redirect light at will, or as shown on the right, we can pattern very finely nanostructures over large areas to make these beautiful paintings where every little color is associated with the presence of a different type of metallic nanoparticle. One big moment for our group was when we started realizing that not only metallic nanostructures can give rise to these beautiful colors, but also semiconductor nanostructures, as shown below for the famous semiconductor silicon that forms the basis of all semiconductor electronics. Here in the bottom, one sees how when we illuminate with white light nanostructures that are just 30 nanometers in diameter, we can achieve a blue color. And if we grow the diameter to the right for these nanowires to about 185 nanometers, we can see a red color. And different sizes in between can give us all of the colors of the rainbow. Now already Gustav Mie in 1908 wrote a famous paper about light scattering from dielectric spheres. Here we use it now, something new, for very high refractive index semiconductor structures. High refractive index means that the material responds very strongly to light and polarizes very easily and scatters strongly, very naturally. But depending on the size here, we can achieve different resonances. And this we may be able to use to build new types of optoelectronic devices. To understand how these resonances in the nanowire work, it's interesting to think about an acoustic alternative to the resonance that happens in these nanowires. Already a long time ago, in 1878, Lord Rayleigh was able to describe that in the St. Paul's Cathedral, if you go up into the dome and sit at the edge of the dome and start speaking or whispering very gently, the sound waves could travel all the way around the dome. They would cling to the side wall and slowly bounce around in a circular motion path, as you see on the right, shown in yellow in the bottom view of the dome. In circular path, it could go around the dome. Well, it turns out that light can do the same thing. Light, if you sit in a glass medium, for example, with a refractive index of 1.5 and surrounded by air on top, then light can totally internally reflect from the interface between glass and air. This gives rise sometimes to annoying reflections when you're wearing spectacles. Now, this total internal reflection one can use, as shown in the middle image, to guide light around the circumference of a microsphere. Here also the light is trapped inside. It's fed by a tiny little glass fiber that you can see vaguely in the background, and then it starts circulating around the circumference. On the right you see a computer simulation of the magnetic field of this light wave that circulates around the circumference here of a glass sphere with a radius r. Now one can get a resonance. One meets an intuitive resonance condition where an integer number m times the wavelength inside the glass fits fully around the circumference, 2 times pi times the radius. Here the effective wavelength is really the wavelength in air divided by the refractive index, because in this glass medium the wavelength shrinks a little bit, and that's why one can resonate it nicely in a smaller sphere. Now resonances occur when this resonance condition is met, because light that has gone around once nicely can constructively interfere with light that has gone around a second or a third time. All of these waves nicely go in unison. We'll talk more about this phenomenon of constructive interference that helps us to build resonances inside these type of dielectric materials. Now, if one looks at the same thing, not for a microsphere, maybe the diameter of a hair, but something much smaller, a nanowire of semiconductor silicon, one can use the fact that silicon and other semiconductors can have much higher refractive indices, maybe 4, 5, or sometimes even 6. And if you have such a high index, even in a small structure that's just maybe 50 nanometers in diameter, so 1/10 of the wavelength of light in free space, light inside can still resonate. Here's the cartoon picture where light comes in to a nanowire, shown here in gray, and it can start coupling into the wire and by total internal reflections, it can start making circular paths. If one solves the famous Maxwell's equations to see what these light waves will look like, that's shown on the right, where you see the electric field of waves where just one wavelength, 2 or 3 wavelengths fit around the circumference. So these are some of the smallest whispering gallery mode type resonators. And we can use the circulation of light in the semiconductor to enhance absorption or to enhance scattering, depending on the wavelength of light. One very nice thing is that no matter what nanostructure shape, whether you take something with a square cross-section, hexagonal, circular, triangular, all of these nanostructures display these resonances and allow light to bounce around a little bit inside the nanostructures to boost light-matter interaction, to get enhanced absorption, scattering, or possibly even emission if it's a light-emitting nanowire. One can see these resonances, as I showed you now a little bit more technical detail, when we look at the nanowires and put them underneath a microscope objective in a microscope, as shown on the left, where we can illuminate the nanowires with white light, and depending on the size, they'll appear red, green, or blue, as I shown you before. Now I want to re-emphasize a very important fact here, that depending on the size of the nanostructure, we can selectively interact with blue, green, or red light. So it turns out that the shape and the size of the nanostructures is starting to become as important as maybe the material, whether you use silicon or germanium or titanium dioxide, different semiconductor materials. The shape and size becomes as important as the material that you're using. So by design, smart engineering, we can now make devices that can take advantage of this. Here you can see more quantitatively how the scattered light looks as a function of the wavelength, more or less from the blue part of the spectrum to the red to the infrared. And you can see, depending on the diameter of the particle that's listed here, one can see that resonances may occur in the blue, the green, the red, or even bigger wires have multiple resonances, such as in the 185 nanometer wire, where resonances occur because we can fit 1, 2, or 3 wavelengths around the circumference. We can start now using this in true devices. Here is an example where we use resonances to make a truly nanoscale detector more efficient and sensitive to any wavelength or color of light that we want. We know very well from the semiconductor industry and optoelectronics that making devices smaller is a good thing typically, because we can make devices higher speed and have them consume less power. Well, that's wonderful from an electronics perspective, but what about the optics? As we move and make our nanowire devices smaller and smaller, as shown maybe in a schematic on the left, where we hooked up a germanium wire between metallic contacts, and in the electron microscopy image shown in the center. As we move to these smaller devices, it becomes very hard to focus light on them. In fact, there's a fundamental limit to which one can focus light with a microscope objective, which is called the diffraction limit. One cannot focus light to roughly half the wavelength of light. So for green light with 500 nanometers, that would be about 250 nanometers. Much bigger illumination spot here shown in red than the size of the nanowires we can make with today's lithography. Well, will all of the light miss this wire since the spot size is so much bigger than the wire? Well, it turns out resonances can come to the rescue. If you do this experiment for a germanium nanowire, it has a very nice high refractive index, and you plot the photocurrent, which is produced by light being absorbed in the wire to produce excited negative electrons and positive holes that we can pull apart via the electrodes to produce current. If we plot that current versus wavelength, for different nanowire sizes, again, we see resonances. Small wires resonate in the blue and green part of the spectrum, and bigger ones can show multiple resonances, where the light interaction or the absorption is enhanced by fitting light maybe wavelength once, twice, or 3 times around the circumference. Every time then, due to the fact that the light circulates inside the absorbing medium, like in a solar cell medium, we can make bigger photocurrents happen. So it's wonderful that we can use resonances that naturally occur at the nanoscale to make devices more efficient. Let's see whether we can take the next step for the semiconductor building blocks and make large area structures that we nowadays call metasurfaces. Well, on the left you have your scale bar again. We see our favorite material, silicon, which on the scale, the macro scale, when we make tens of centimeter silicon wafers and polish them, they look mirror-like. But if we break them up in tiny little nanostructures, we see these beautiful colors. Now these are, again, building blocks from which we can make more complex systems. These nanowires we can assemble together in, for example, a beautiful little flower, where the red, green, yellow, and blue colors come from light scattering, white light scattering from nanowires, but each different nanowire diameter gives you a different light scattering color. So we can start building libraries where, if we understand the light scattering from the different structures by themselves, we can build bigger constructs, metasurfaces out of the building blocks, meta-atoms, and achieve interesting optical functions over large areas. Now this is done with semiconductors. Semiconductors, as I said, are the basic building blocks of all sorts of devices. Here you can see examples of devices that we use on a daily basis. Our cell phone that makes beautiful colors from our display, or image sensors in cameras from which we can take images of the world around us, or solar cells, or semiconductor lasers. They're all built up out of semiconductors. If you look inside those 4 different types of devices, you'll see in cross-section that all of these devices are built up out of layers. Look at, for example, the bottom left cross-section of a solar cell made by my postdoc advisor, Harvey, where we have metals and semiconductor layers and insulators that are all continuous typically, and made by depositing thin films on top of each other. What if we could take one of these layers and structure it below the wavelength of light? Could we manipulate light absorption or light emission in a semiconductor laser? Could we get new types of absorption spectra just by manipulating the structure rather than changing the materials we're using? If so, then it should be possible to make devices that operate at lower power, have new types of functions, could possibly operate at higher speeds, and provide entirely new opportunities and functions. Here's an interesting example where we made a metasurface out of germanium wires. All of these germanium wires can show resonances and change the optical property of the film. On the left side, you see a scanning electron microscopy image of a germanium film, just 50 nanometers in thickness, that we patterned by electron beam lithography. And we can illuminate this film with polarized light, where the electric field is either along the wires or orthogonal to the wires. And based on the anisotropy in this sample, you might expect a different optical response if the electric field is along the germanium wires that light up a little brighter than the background, or when the electric field is orthogonal. On the right side, you see white light reflection images, both of the continuous film, in this case of germanium, looks a little grayish, and that's because germanium absorbs broadly across the visible spectrum. But if you have the electric field along the wires or orthogonal, you see very different behavior. When the electric field is orthogonal, it looks a little goldish, which is the substrate, mirror-like substrate that we have underneath, that you can see through the bars of germanium. But on the right, when we align the electric field along the wires, something spectacular happens. We drive a resonance, and actually the film goes black. So note that in going from the continuous film, by removing about 2/3 of the material, we achieve more absorption. It goes from grayish for the continuous film to black for the nanostructured film. And this is due to the fact that the thin film has weak Fabry-Perot resonances, whereas the nanostructured wire-based metafilm has optical whispering gallery mode resonances, where the light much more effectively circulates inside the wires and causes much stronger absorption. So it nicely shows that by nanostructuring materials and using our knowledge of resonances, we can really boost absorption. This may be great to make a solar cell more absorbing to produce more photocurrent. I'll show you some other examples. Together with the Samsung company, our group worked on nanopatterning metallic electrodes that can inject current to make beautiful red, green, and blue colors from our display. In this case, we didn't use color filters as is typically done, but we did achieve this by just patterning the metallic electrode with tiny little metal pillars to allow a change in the reflection phase of light of this mirror. Let me show you what I mean in cartoons over here. Well, on the left side, you see how in the olden days we used red, green, and blue emitters that we clamp between two mirrors, one top mirror quasi-translucent to let light out, but we used the phenomenon of resonance to boost the light emission in the blue for small mirror spacings. For a little bit bigger spacings, we could resonate the larger wavelength of green, and for even bigger spacings, we could start resonating red. Now, over time, it became very hard to shrink to smaller and smaller pixels to make more high-resolution displays, and that's why people went to color filters, here denoted by CF. We just had red, green, and blue color emitters and used color filters to selectively let green, red, and blue out of this light-emitting diode, or OLED, organic light-emitting diode. This is a nice concept, but color filters absorb a lot of power. Wouldn't it be nice if we could do even better? And there on the right, we got back to these cavities, where now we could deposit continuous films of red, green, and blue emitters. But by having the same mirror spacings, but going to meta mirrors, we could manipulate the reflection phase and actually allow a resonant pathway to be set up for all the different mirror conditions, just by manipulating the reflection phase in different ways by having tiny little bit different pillars on different meta mirrors. So here, no light is lost due to absorption, and we could keep on continuing the scaling of these displays to smaller and smaller sizes of pixels or higher resolution. Here's another nice example where we try to apply our knowledge to solar cells, where we covered the surface of a solar cell with tiny little particles that are shown on the top right. By having single-sized silicon nanoparticles on top of an otherwise beautiful, smooth silicon solar cell material, we could get anti-reflection or low reflection as shown in the graph, where we plot the reflection versus wavelength at one wavelength, but actually having two different sizes of scatters. These different sized particles could manipulate the light scattering such that the reflection of the silicon solar cell could be cancelled by the big ones, big particles in the redder part of the spectrum, and the smaller particles could take care of the anti-reflection at the shorter wavelength of the spectrum. So this enabled entirely new types of anti-reflection coatings, originally inspired by my PhD advisor, Albert Pullman. Let's see whether we can take the next step. whether we can not only make beautiful colors or make better devices for light emission and absorption. Let's see whether we can start constructing devices that can manipulate light waves, steer light waves, focus them, and maybe even steer light waves dynamically to make, for example, dynamic holograms. Here we harness the fundamental processes of light scattering and interference effects. Already in this example where we dropped two little stones in the water, you can see water waves emanate from the location where the particles hit the water. And you can see all sorts of complex, what are called interference effects, where the waves produced by each of these particles can add up or destructively interfere with each other. Let's look at that a little bit more quantitatively. On the left top image, you see two fishermen that are bobbing their fishing rods in the water, producing outward going water waves or rings, just like the two stones that were dropped in the water. Now, if you look very careful at the patterns of the waves that are generated by these two fishing rods, you'll see interference effects. You can see on the top right a very complex patterns where certain direction light waves travel, but also certain directions it seems that the water is completely still. And to understand that, we need to use the concepts of interference and the concepts of phase. Phase is basically tells you where waves have their highs and lows. It turns out, as bottom right, if we have two waves that have their highs all in the same location, actually the amplitudes can add up, and you can get a very strong oscillation. If in some cases two waves propagate in parallel, the highs and the lows are not aligned, then we get a process of destructive interference. This is where the light isn't going. So from this example, we can learn that we can start manipulating where light goes by manipulating interference effects. So this has truly enabled an entirely new way of making optics. We're used to making optics by polishing beautiful pieces of glass or molding pieces of plastics to make lenses or prisms that can focus light or redirect light at will using the fundamental laws of refraction of light that can happen at interfaces between, for example, air and glass. We have moved to a completely new type of optic that's studied by many groups around the world at this moment, called metasurface optics, where we just deposit a very thin layer of metal or semiconductor and then pattern it into these tiny little light scattering structures. And if we can control, by changing the size and shape of these, the amplitude and the phase of the light scattering, we can achieve the same functions as the optical elements that you see on the left. But in doing so, we do something very special. We're completely decoupling the shape of the optical element from the function. In a lens, the curvature of the glass determines the focal length. But on the right, we have a perfectly flat optical element that actually we could integrate easily with electronic devices that are also naturally planar. This will give many new types of advantages where we can stack electronics and optics directly on top of each other. And the challenge of making such optical elements is not in the art of polishing glass and putting anti-reflection coatings on, but entirely new design where we need to learn this art of how do nanostructures of metals and semiconductors of different size and shape scatter light, and how do we pattern them over very large areas. Then we can make truly commercial, viable new types of optical elements. To illustrate how these optical elements work, we know how a conventional lens works by bending beams of light, refracting beams of light at interfaces between glass and the surrounding medium. That allows focusing. There we use a thick optical element that typically is heavy, maybe millimeters in size. But instead, as shown in this paper by Federico Capasso's group, we could just nanostructure elements on a glass substrate, as shown in the scanning electron microscopy image on the right. And by carefully studying how each of the nanostructures scatters light, we can again achieve the same focusing function. Each of the nanostructures here color-coded in the bottom image scatters light with a different phase. And in doing so, constructive interference again can happen in a focus. So you can see the power of this, that we can start making nanostructures of any type and make any optical elements at will. Maybe prisms, maybe lenses, maybe new types of things. Here's an example from our group where we've gone from bulky lenses to making completely flat optical lenses, enabling the same function. But then also, as shown on the right, we can enable entirely new functions. We can pattern in complicated looking structures here in scanning electron microscopy image of silicon nanostructures that look in almost spaghetti-like shapes designed to scatter lights in such a way that this optical element encodes 3 different lenses that can take optical pictures from 3 different vantage points to allow something which is called light field microscopy. Here we can take images and, for example, refocus after the fact, even after the image has been taken. Or we can build an optical element as shown on the bottom right, where we have a white light S object, Stanford S, and the optical element actually not only focuses the image back to a nice, beautiful image, but it does so separately for the blue, green, and red components of the light that sit in this image. So new types of things are possible that are very hard to achieve with dielectric lenses or glass lenses. And it's interesting to become creative, and we have an entire community that does so, to see what all we can do with these type of optical elements. Now, I've told you the story of building flatter and flatter optical elements, and I should definitely acknowledge the fact that we're certainly not the first to try and push to thin optical elements that can do new things. On the top left, you can see in the 1970s, a year after my birth year, people already made DOEs, diffractive optical elements, that look like Fresnel lenses, where light was steered by making topographic features in the surface of glass, to new types of optical elements called binary blaze gratings, the precursor of maybe metasurfaces, where tiny little pillars of titania, dielectric, of different size, could enable different phase pickups and allowed us to steer light just like a prism. And you can see the image gallery evolve to new types of structures and ever better control over the size and shape of structures as our fabrication tools and simulation tools have improved, all the way to the topic that I wanted to highlight today, that one can use atomically thin materials to dynamically steer light. Now, there's a tremendous promise for this. If we can make optics flat, lightweight, we can stack these structures on top of each other, we can integrate them with electronics, maybe we can do it low cost due to ever increasing ability to fabricate nanostructures at scale. And there's also a nice thing about sustainability. We can now make optics where it's really the shape of the structure that matters as much as the material that we're using. So we've been able to start using much more environmentally friendly materials to make this type of optics, scale them to large sizes, and also enable more effective recycling of these materials. There are, of course, challenges. They are shown on the right. How do you mitigate aberrations? How do we achieve very strong light matter interactions with these small structures so we can get efficient optical elements even when they're so thin? Can we make them power efficient if we make them dynamic? Can we achieve the high quality of patterning over large area? These are all things that are keep being developed to make the technology better. One question that our group asked was to say, can we also make these elements dynamic? If we can make them dynamic, we can not only passively focus light to a spot, but we could make displays, dynamic imaging systems, beam steering systems for LiDAR, self-driving cars, three-dimensional holographic images, neural networks, that maybe ultimately can mimic or assist the electronic neural networks that we have. There we need to have high efficiencies for manipulating light. We want to steer things over large area, meaning high numerical aperture. There are many questions of how to hook up these tiny little nanostructures that are going to dynamically steer. And how do we do it even? How do we make meta-atoms that one can change dynamically? Well, here I'll tell you how we can actually make these meta-surface devices dynamic, how we can allow them to steer optical beams actively as we apply maybe electrical currents. On the left is one example where we used in our group mechanical motion. There we have silicon nanowires, as you see in the tilted electron microscopy image, where we can move them above a substrate to dynamically steer optical beams. In the center example, we use phase change materials. They can change their refractive index and thus their resonances by going from a structurally amorphous to a crystalline phase. These materials, like germanium antimonide telluride, are known from compact discs where one can write with light flashes optical bits of information into the disc. In this example, we actually use a silver nanowire to not only as a scattering element, but also to heat the phase change material shown in red sitting on top. That allows us to, with little pulses of heat, change the structural phase back and forth and tune the scattering properties. I'll show you this example in a second. On the right, we also show that excitons, materials excitations inside semiconductors, can be used to focus light and to modulate it very effectively. Here's the example of the phase change material. This phase change material can switch between two structural phases, a crystalline and an amorphous phase. And the key thing is that these phase change materials allow a order of unity refractive index change between the two phases. That notably can allow us to tune the scattering properties of the nanowires. In the center you see an electron microscopy image of our device where we have a little metallic wire and contacts where we can drive the electrical current pulses, but then also on top of that wire sits a phase change material wire, GST, that changes the scattering properties through its change of the refractive index. On the right is what you would see in our optical microscope in the dark when we illuminate our wire with white light. It changes its scattering properties as we run these different currents through the metallic wire, pulses of different duration and length to allow you to tune the scattering of the wire. Okay, how are we going to make these devices faster and even more compact? We've learned from this nice example, one from Federico Capasso's group on the left, one from our group made from silicon nanostructures in the center, that these nanostructures of metal and semiconductors scatter light very efficiently, already shown by Faraday. But it's very hard to tune the optical properties of these metals and semiconductors that are most commonly used. So wouldn't it be wonderful if we could make things that tune fast and possibly even go to very thin scales? In our group, Jorik van der Groep nicely showed that if we go to the atomic scale, new opportunities come along when we make semiconductors so thin that they start supporting very strong, what are called exciton resonances. I'll discuss these more, but it turns out that these materials resonances, excitons, dominate the optical spectrum in the visible. They produce very nice sharp peaked structures, and they offer some of the fastest light-matter interaction that can be tuned that we know of in optics. Here is an schematic example from my colleague Tony Heinz, where we have a two-dimensional layer of semiconductor, actually here composed of 3 atomic layers, such as, for example, MOS2 or tungsten disulfide, where if we illuminate them with light, we can excite an electron to a high energy level, and a positive charge leaves behind, and the positive and negative charges can bind to each other, forming a bound electron hole pair, or exciton. If you look at the absorption spectrum of such a thin film, then you can see the ability to excite excitons as a very sharp resonant feature called the exciton peak, far away typically from the absorption across the band gap of the semiconductor. Now, as an optics person, I was looking at images like this, absorption spectra, thinking this is a beautiful resonances. Can we harness them like the resonances, Plasmon resonances in metal and whispering gallery mode or me-type resonances in semiconductor? Can we use them in the same way? If so, we may be able to make atomically thin optics that can switch and redirect beams extremely fast. This was one of the experiments that really inspired me to think about working on this topic. It's two papers that simultaneously came out from a group in Harvard and ETH that showed if I illuminate a very thin layer of atomically thin semiconductor, in this case molybdenum diselenide, at very low cryogenic temperatures, 4 Kelvin, then it turns out, as shown in the center image, this little flake, although it's atomically thin, can act as a fantastic mirror. It very efficiently reflects the light with which it's illuminated. But if you inject a little bit of current into this two-dimensional semiconductor, it turns out, as shown on the right, that the flake goes dark. And this is because the electron hole pairs break up. They are no longer excited by the light. The resonance disappears. Well, that's wonderful. We can make a mirror that we can turn on and off that's atomically thin. Can we not only make a mirror, but maybe a lens or other metasurface-based optics that could steer beams? This set us off, and this is work by Jörg van der Hoop, to make a tiny little island of tungsten disulfide, one of these atomically thin semiconductors. I've outlined it here with a dashed line because it's hard to see such a thin film in invisible white light reflection. This is at room temperature. At 4 Kelvin, maybe it would have been more reflective. There's a little trench around it, and we can shine light and take a reflection measurement. And indeed, even at room temperature, if you look at the reflection, here the reflectivity is about maybe 3 to 4%, so not as amazing at 4 Kelvin, but we see two very strong resonances in the blue curve if we don't apply any voltage. If we inject a little bit of charge, similar to the experiment by ETA and Harvard, there the resonances completely disappear. This was amazing to me, since never resonances of metal nanoparticles or semiconductors we can completely turn off. So this came with the question, can we actually make resonance that we can turn on and off quickly to scatter light on demand? Maybe we can tune resonances by changing the properties of the semiconductor, tune them spectrally as well, and manipulate the scattering phase and amplitude at will. Where here is a optical measurement on one of these atomically thin lenses that we put in a special microscope called a confocal microscope. There we look at it, the lens, with a microscope objective and capture the light in a fiber that goes to a detector. Then we illuminate it from the back to see whether we can see the light come to a focus. And a little piezo mechanical stage allows us to move the lens underneath the microscope objective and see visually how the light comes to a focus, as shown on the right. So this worked. An atomically thin lens can focus light. Looks very promising, but unfortunately the efficiency turned out to be only about 1%. So new question come up, can we make it better? Well, in going back to the earlier work on the highly reflective atomically thin mirror, it turned out there the reflectance was great at 4 Kelvin, or really low temperatures, but as we increased the temperature to room temperature, about 300 Kelvin, the reflectivity completely dropped. So here's a wonderful opportunity for physicists and clever engineers to see whether somehow we can regain that beautiful reflectance and all of the wonderful resonances and optical properties at room temperature, so we can harness them in real devices. And this is part of our proposed effort where we're going to spend the prize money to build new types of atomically thin devices. We hope to see whether we can impact the challenges of what are called dephasing and non-radiative decay that limit these atomically thin quantum materials. Dephasing and non-radiative decay basically means that these exciton resonances become unstable at room temperature. For example, because lattice vibrations at high temperature cause them to fall apart. These are these unwanted dephasing and non-radiative decay processes. But we have solutions, and there's a large materials team and physicists and engineers working on this to not only go to low temperature and see this, but to enable room temperature operation by improving the growth of these materials, by heat treating them, thermally annealing them. Chemical treatments can place atoms that were missing in these two materials back in and make them more efficient reflectors and scatterers of light. We can encapsulate them to protect them for the environment. We can stretch them to change their optical properties, and we can apply one of our favorite topics, nanophotonics, for example, bringing in metallic structures close by these 2D materials to enhance the light-matter interactions, for example, using plasmons. Now, there's a larger opportunity here as well for the larger 2D and optoelectronics community to see whether we can harness not only the exciton resonances that we've seen, but there are also lattice resonances, phonons, lattice vibrations that maybe we can harness to manipulate light. We can also maybe use plasmon resonances, not in big metallic particles, but atomically thin layers of graphene. I think an entire field is starting to open up with many players where we can start harnessing not only metal nanostructures, semiconductor nanostructures, but also these beautiful two-dimensional materials and see whether we can start applying them more in optics. Well, let me close by pulling up my first slide where I showed you all of these wonderful technologies from solar cells to displays and augmented reality. I think having hopefully shown you that the resonances can play an important role in metal nanostructures, semiconductors, and even atomically thin materials that support materials resonances. Can we continue in quest to make all of these devices, technologies better and see together as a community we can attack these important problems? Thank you so much for listening to me during this Harvey lecture. I very much look forward to answering questions next. Thank you.
Well, hello. I'm Sir John O'Reilly, and I'm chair of the Search and Selection Panel for the IET A.F. Harvey Engineering Research Prize. It's my pleasure to welcome you to this year's Harvey Prize lecture, Dynamic Control of Light Waves with Atomically Thin Optoelectronic Devices, just delivered by our prize winner for the 2025 prize, Professor Mark Brongersma. And what an excellent, thought-provoking lecture that was. Before the lecture, you'll have seen a short film about the history of the prize and some of our past winners who've all gone on to achieve really outstanding things. The prize, an impressive sum of £350,000, which is probably approaching $400,000, I guess, in the US, set up in 2010 with a trust fund from the late Dr. Arthur Frank Harvey. It's awarded annually to an outstanding researcher working in one of three broad fields: radar and microwaves, lasers and optoelectronics, or medical engineering. And this year, of course, it's lasers and optoelectronics or photonics. And it's for them to use flexibly to assist their ongoing research program. Our search and selection panel looked globally for potential candidates, drew on their extensive networks internationally to reward the most innovative researchers in the field. Mark is a professor at Stanford University, where he leads a lab on the development of optoelectronic materials and the materials and devices. He is a recognized world leader in the field of nanoscale photonics, the science of controlling the flow of light at incredibly small scales. And he's the 15th winner of the prize. So congratulations, Mark, and very good to have you with us for this Q&A session. A well-deserved achievement, and actually a very impressive lecture indeed. As I said, 15th winner, but you've had the lecture, so let's get started on the Q&A. Mark, I'll mix in questions that come in online, but also I'm part of the audience, so I shall feel free occasionally to chip in with things that I want to ask you. But let's start with one that came in online now. Someone's asked, do you see the ability to dynamically adjust the metasurface optical result in real time? Is that something you're working towards?
Yes, we definitely are. So first of all, thank you so much for having me here, and I'd like to thank you for the wonderful introduction and the viewers for following the lecture. Our group is very interested in learning how to not only manipulate light scattering from static structures, tiny little metallic or semiconductor particles, but also very interested in making these scattering processes dynamic. So to do that, we need particles that can change their size, shape, or optical properties dynamically. And one nice example that was briefly noted in the lecture is the use of phase change materials. So phase change materials are known from, for example, recording devices like the DVD or the compact disc, where you have materials that when you illuminate them or run electrical current to heat them up briefly, you can change their structural phase, and that comes with very large changes in an optical property, the refractive index, and that then automatically can change the light scattering properties. So we're very interested in building device architectures where over large areas we can scatter light, dynamically change properties, and that can be applied in, for example, holographic displays or projectors or LiDAR. In fact, one of the previous winners of this IET Harvey Prize, Arseny Kuznetsov, has spent a lot of time building some of the most amazing light steering devices.
It's interesting, Mark. Thank you. In fact, one of the other questions came in, I think you implicitly answered, but it said, how about moving holograms? I mean, holograms are one thing, holograms that move, and that seems to be, at least in your thinking, long term.
Definitely. This is one of the holy grails in our field, to control images like the ones that are coming from your display, but get a three-dimensional feel to them. To do that, we need to not only manipulate the color, but also the angular distribution of light, so we can make holographic type displays that could dynamically move, as seen in Star Wars, but hopefully soon in a theater near you.
That really would be wonderful. And it's interesting you mentioned Arseny Kuznetsov. He won the prize maybe around 10 years ago now, something like that. And that was for his work on dielectric nanoantennas on semiconductors, on silicon. And you made mention in your talk that you'd moved on to something, not that, but similarly moved on to looking at semiconductor materials for your things. Tell us a little bit about the relationship between these two different approaches and how they contrast, how they work together, maybe complement one another, would you?
Yes, I definitely can. So Arseny was one of the early pioneers, I think, for which he won the prize, to understand light scattering from high refractive index semiconductor structures. And interestingly, if you take something like a silicon wafer, which is the basis for the electronics industry, and you start breaking it up in tiny little pieces to make nanoparticles and nanowires, they can scatter light very effectively. but the scattering properties will depend on the size, exact size and shape of these structures. So with the coming age of nanotechnology, people have been able to more and more accurately control the size and shape of these structures and thereby control the way they scatter light. By changing size and shape, we can change their color and we can change the way they steer light. And Arseny Kuznetsov was a early pioneer in cataloging and trying to build physics models to understand that light scattering. Our research was complementary to that, where we tried to pattern nanostructures in devices such as photodetectors and solar cells, or also even displays, where we wanted to see whether we can control the way the light flows into a solar cell, maybe gets redirected in the plane of the solar cell to enhance light absorption or to reduce reflections. Similarly, we controlled structures inside displays with large companies to see whether we could make more efficient displays, and ultimately working towards this holographic display.
Very good. I think the other thing that struck me when I was reading about it and also listening to your lecture is there are other things that happen. Surfaces into metamaterials led to metasurfaces and so on. And we don't automatically say plasmonics in there. Again, a relationship there perhaps, and something you could expand on?
Yeah, very nice. So the world of metasurface optics is a field where people have first learned how light is scattered by individual nanostructures, and then with novel techniques like nano imprint lithography or the lithography used to make semiconductor chips, we've been able to make such structures over very large areas. And if we can control the scattering amplitude and phase of all of these structures, we can mimic optical functions of, for example, a lens or a prism, something that manipulates the flow of light, but now instead of using refraction of light through curved surfaces like those of a lens, now we harness light scattering and interference to do the same thing, focus light, redirect light, but now also make things dynamic. So the wonderful opportunity that comes with making flat optical elements based on metasurfaces is that these things are more lightweight because they're planar geometry. They're easily integrated with planar semiconductor electronic devices, and now also we can start tuning those devices dynamically, which is very hard to do with conventional lenses to change their focal length, for example. So that's why there's always mechanical parts needed to make, for example, a zoom lens happen.
So another question that's coming online to me relates exactly to what we've just been talking about. They ask, could you use light to control light in this technology? And of course, that's what you're talking about. But I've heard it said, of course, that when plasmonics got started, it was with metals, and with metals, you have loss. And one of the things I think that Arseny thought is quite attractive about the work he did was with semiconductors and the nano antennas, that was not such an issue. So maybe you could talk a little bit about how the loss plays into this and the things that have changed over the time as you've gone through your work on this.
That's right. Well, I was very fortunate to be very early in this field of light manipulation with metals that's now called plasmonics, where people try to harness light scattering properties from metallic structures and also try to guide light along metallic wires. Typically that's done along glass fibers that are beautiful and transparent, but early 2000s people found out that one could focus light to truly the nanoscale, the same scale as transistors or electronic circuit elements. And although there's a little bit of loss manipulating light with metals as they drive electrical currents, and that causes heat generation, often one can think of devices where the benefits of using light concentration with metals far outweighs the little bit of loss that occurs as you manipulate light with metals. For example, we were early in developing photodetectors where metallic leads are needed to hook up a tiny little photodetector but at the same time, these metallic leads could be designed as antennas that concentrate the light into a much smaller photodetector than would be possible before. Because typically one is limited by the laws, fundamental laws of diffraction. One can't focus light into a tiny nanoscale structure as small as a transistor. But now you could use the metallic leads that hook up the photodetector to also concentrate the light in that photodetector, making it higher speed, lower noise, lower power, electrical power consumption. So, Arseni nicely pointed out that came maybe a decade or so later, that one could manipulate light without loss if one operates with photons or light waves that have energies that are below the band gap, so you can't excite electronic excitations in these semiconductors. So suddenly there was a whole toolkit of nanostructures available to manipulate and scatter light without loss, which was a big problem with plasmonics. But at the same time, our group was very excited to capitalize on the light absorption and emitting properties of these same semiconductors and use the resonances in those structures to make better photodetectors, light sources, and things like that. So lots of developments by many great groups in our community, sort of early 2000, and then also going on from Metasurfaces to 2010 to now, still going on.
Yeah, and it's interesting how those things now are complementing one another in the approaches and so on, I think, really. Yeah.
That's right. So we've become in the last 2 decades very aware where it's helpful to manipulate light with metals or with semiconductors.
Yeah.
So both have their relative advantages for different technologies.
Another rather different question has come in now. Is it possible we can see this technology benefit in future, especially for energy efficiency, if we start looking at where it might go? Is there anything any thoughts you have along those lines?
Yes, yeah. So in 2 different ways, there are impacts of energy efficiency. So we have used some of these nanostructures to concentrate light in photodetectors or solar cells and made them more efficient by patterning an array of tiny structures on a solar cell. We could capture light in much thinner solar cells concentrated in these cells, and we've made up to about 15% efficiency silicon cells that are just a few microns in thickness. We've been able to more efficiently deliver light to molecules and manipulate chemical reactions. So there's an interesting efficiency enhancement in light delivery to molecules for reactions. Sensing mechanisms can be enhanced by concentrating light. Light in reverse can be more extracted efficiently from display elements. So not only in energy harvesting there is a big benefit, but also in the energy efficiency of displays. If you touch your TV, it's a little warm due to the inefficiency with which light gets emitted, and some of the light never makes it out to produce heat in your TV or display. So there are efficiency enhancements as well in many optoelectronic devices, possible by controlling better the flow of electrons and of light.
Yeah, well, it is interesting. It's fascinating to me the way that things mix and move together. I mean, the work you first did with metal and nanoparticles, and I think I'm right, aren't I? You came up with the name plasmonics. Is that right?
That's correct. This came out of a discussion with my postdoc advisor, Harry Atwater. He said, "Mark, you need to come up with a name, as we are transporting optical signals along metallic structures. We saw this as akin to trying to guide electron signals currents along metals. So we thought we need to think of something that sounds or does like electronics, and ultimately, together we came up with this word of plasmonics. I made a list of 20 different names, and the plasmonics one. Yeah.
I think it must be particularly exciting as a PhD student or a postdoc when you've got something you say, you know, we have to think of the name for this. And then that name goes on, and that really is quite.
This was very special. Yeah, yeah. My postdoc advisor Harry Atwater said, if you name it, you own it. You can then people will start to talk about it in a new way as a real technology. And it was very nice to see that suddenly there's symposia or conferences that are called plasmonics, and it becomes a thing, you know, a new way of thinking about it. Like metamaterials was a new way of thinking about.
Yeah. And it was a very busy time in the community at that time once that came out. And I think the name plays its part in generating the interest and so on, which is why I sort of mentioned it. Yeah.
That's right. That's right. And well, that's the importance of translating interesting ideas to a larger community. So that's one of the reasons I'm very excited to be part of this lecture and think about how to educate and get broader communities excited about this work.
Yeah, and one of the reasons I mentioned earlier on, I mentioned metamaterials, Arsen's work, but also metamaterials, metasurfaces, and so on, is increasingly these things work together, it seems to me. So I'm very much a practical engineer, or used to be. So I look at, okay, now what's this good for? What can you use it for? What's coming? And one of the things that seems to be coming is in telecommunications, sixth generation, 6G. You know, we're familiar with 5G, work on 6G. And included in that, because they move at much higher, want to exploit the higher frequencies particularly, you know, going into the terahertz region, then reflective surfaces and manipulative reflective surfaces are very much in the thinking and so on. There are a range of technologies that could do that. How does this play in there? Does this play in there to some degree? Perhaps you could give that.
Yeah, no, I think it's actually very exciting that the fields of radio frequency and terahertz and optical manipulation of light waves are all now considered together by a growing community. These communities were maybe a little bit more separated, let's say, half a century ago. Now ideas from the different fields and different frequency regimes are translated, and this is in part in the beautiful scaling properties of the famous Maxwell's equations, that if you get an idea in one frequency regime, you can apply it. Similar types of interactions of radio waves with matter happen as light waves with matter. But also design principles come. So the dynamic reflective surfaces to maybe steer terahertz or radio signals dynamically to get signals to someone working in a coffee shop are very similar to now steering light waves for example, augmented reality to directly write images into the eye, or scan laser beams for self-driving cars to scan the environment. So yeah, for telecommunication, for sensing, all of these technologies now, this large electromagnetics community, from radio waves to terahertz to optical, can all learn from each other. And there's a lot of interaction there, both in exchanging ideas on what materials should be used, what principles can be harnessed. So for me, it's a very exciting time because I'm always looking for new directions to learn. And in fact, a lot of the ideas we are working now have history back to artificial dielectrics or reflective surfaces at longer wavelength or lower frequency regimes that we're now able to apply, because we can make these tiny structures that are better at manipulating the shorter wavelength of visible and near infrared light.
It's interesting that you mention artificial dielectrics, of course, because in a way that was a forerunner to the metamaterials. And
that's right.
In some sense, and actually Harvey was at the Royal Radar Establishment, and there was certainly work on that going on then. Not with the foresight that says, oh, we could do things with things that become called plasmonics or nano antennas or even the intricate structures that we see in metamaterials. But nonetheless, it is interesting how things join up. And
that's a fantastic history. Yeah, many things, many of the thinking started there, really. So it's nice that that traces back to Harvey.
I have a question here that's coming now that takes us back down to the materials stuff right in your, right in there. Asking if there are any comments on possibilities of using transition metal calcite. I have trouble with pronouncing calcite.
Dichalcogenites,
you know what I mean, TMC.
I have the same issue.
It's anchored on, I think it's titanium dioxide and strontium, titanium, and so on. Any results based on such materials in the nanoscale? Do you see prospects there?
This is actually one of the things we're very excited to study with the prize funds, which allow us to really go in an entirely new direction. So a range of atomically thin materials have well, emerged maybe over the last decades or so, where people have looked at transport properties of graphene or transition metal dichalcogenites that are just an atomically thin layer. And interestingly, in these atomically thin layers, people can make metallic structures, they can make insulating, they can make semiconductor structures like the transition metal dichalcogenites, and they show responses that are truly unique to their two-dimensional geometry. Here, because of their extreme thinness, quantum mechanical effects start to play a role, and to our excitement, they show strong resonances. For example, these thin semiconductor layers show exciton resonances within the absorption spectrum. This is just due to the ability to create an excited electron-hole pair. And this, if you take a light transmission spectrum, you see this nice sharp resonance. And we would love to use these resonances like we use the resonances of metallic structures and semiconductor structures to more strongly interact with light and use them the same way to steer light and direct light, emit light. So these materials, like we're very interested in tungsten disulfide, tungsten diselenide, molybdenum disulfide, which also is known as a lubricant between two frictional surfaces. These materials turn out to have amazing optical properties, and we're using these now to make dynamic metasurfaces. We found out that they're much easier to tune by applying a little electric field or stretching the material. We can tune these resonances dynamically. That's very hard to do dynamically with a metallic particle. So we're very excited about those materials in particular.
And that's a very interesting point there, because in a way it really was graphene that drew 2D materials to our attention. And for a while we thought graphene is the answer, what was the question kind of thing. But now there's Mexine and there's much more work in that field. And yes, so in a way it's not dissimilar to what happened with plasmonics, which is it starts there, but then it goes out into different directions. Yeah,
that's right. That's right. Yeah.
Yeah, go ahead. Yeah.
No, it in the early phases of when a new material becomes available, or a new insight becomes there, typically new materials can inspire new technologies ultimately. But in the early days, there's often people that say, no, this is never gonna work, but then creative minds start to work on it. And it's nice to have a team here, about 10 students, that come up with lots of ideas like, can we use this or that material in a new technology? And that's how it starts going, and slowly communities build.
And that's very much something when we formulated the Harvey Prize in the way that we did. He set the broad areas, but we formulated it, and we thought how it could make its best difference was to take someone who had done something, really achieved something, and with the potential clearly to go on and do a lot more, and then give them the funds with freedom. So we don't nail your feet to the floor, as you know, in terms of this is the deliverable and so on, to give you that more freedom to investigate more and to take to really take us into new paths, as they say. So I think maybe with that, that's a point at which we might bring the conversation to a close. It's not the close, it's very much the beginning, we hope, of many more new things for you and your team, and that the Harvey Prize will play its part in enabling that to be the success that it deserves. So with that, Mark, I think I'll just first of all thank you for your lecture and
Thank you
for
so much.
engaging in the conversation, the audience for joining us online, and to remind them that they can claim a certificate for continuing professional development by sending an email to awards@theiet.org. That's particularly applicable to the IET members who are here, who keep up their professional development. And the video will be available to watch again on demand via the IET.tv platform in due course. With that, I'm going to say, Mark, enjoy your day. For those over here, it's more the rest of the evening, and for many of our audience, goodness knows what time of day or night it is, but it's been really good to get together for this talk. Thank you once again.
Thank you so much for having me.